So I guess we'll get started here. Can you hear me okay? Is the audio working? Perfect. So today we're going to talk about Common Industrial Protocol and just kind of an introduction how to get started if you want to do your own exploitation, maybe learning about the protocol, do some basic pen testing, that kind of thing. So let's talk about what is CIP. Common Industrial Protocol is a communications protocol used by industrial devices. So you have things like programmable logic controllers. These are the computers actually in your industrial facilities. They're controlling your plant. They're running the logic, opening and closing valves, turning pumps on and off, looking at sensors. And a lot of PLC systems can communicate via CIP, or they work with other devices in your plant that will use CIP. So examples would be like variable frequency drives, which are the devices that control the speed of motors running in your plant. You have things like motor starters. These would be energizing motors, power monitoring systems, smart sensors and instruments, devices that open and close valves. All of these devices can talk Common Industrial Protocol at one level or another. Now with that, CIP isn't a typical protocol in the sense that we think of for network protocols. It actually extends beyond your Ethernet networks in your plant. So there is versions of CIP like DeviceNet. DeviceNet uses a CAN bus-based system. There's ControlNet, which is coaxial based. Ethernet IP, which is the Ethernet version, and CompoNet, which we're not going to talk about because nobody cares. So originally, it was developed by Allen Bradley, which is a company that builds a lot of industrial hardware, especially in the US. The very first implementation of it was revealed in Chicago in 1994, and it really opened up the world for what was possible bringing data onto the plant floor, how to actually have smart devices in your plant. Before then, you had primitive PLC systems that were all independent of one another. There was a couple of vendors playing around with some serial forms of communication, but it was slow and clunky. And when DeviceNet came out, it opened you up to having very flexible installations of smart sensors and other types of devices than a PLC, able to exchange data in your plant. In '97, they released ControlNet, coaxial based. It's based on the 802.3b specification for its layer 1. So that's your old school coaxial Ethernet. It uses the same type of Manchester signaling on the coax. Later in 2000, Ethernet IP came out. That's Ethernet Industrial Protocol, not to be confused with TCP/IP. And it utilizes both UDP and TCP for transport, multicast, unicast. It's quite the interesting system. Again, nobody cares about CompoNet. So how does Ethernet IP actually work? Let's talk about the SIP stack. You have your TCP and your UDP. You have an encapsulation protocol. That's actually what is Ethernet IP, is that encapsulation protocol. You have different types of messaging, implicit and explicit. Implicit is just a device streaming information. Explicit is a request and a response, single transactions. You have CIP network and transport. CIP is super unique in the sense that it was pre-Ethernet networks in the plant. So they invented their own method for doing things like routing, doing things like CRC checks. Everything that you take for granted that's handled for you at your Ethernet level, CIP has those mechanisms built into it as well. So when running on Ethernet-based networks, yes, you're taking advantage of TCP routing, but you're also taking advantage of CIP's network capabilities, such as CIP routing. And then finally, you have your application objects, your device profiles. These are actual C++ objects executing in the firmware of these devices that CIP hooks into, and that actually gives you the functionality for the protocol, and we'll talk about that. Like I said, objects. So what are CIP objects? CIP objects are fascinating because CIP operates a lot like a remote procedure call type protocol. You have objects in memory in your firmware, and you have a class ID, and that ID number is a unique ID that references that C++ class. You have instance IDs, and they represent the instances of those classes. You have attributes. Your attributes are variables within those objects. And finally, you have your services, which are actual functions in that object that you can call over the network. All of these different things, your class, your instance, your attribute, your service, they're addressed by unique identifiers, integer-based identifiers. So they're not using strings, they're not using names. When you send a CIP request, if I'm telling a device, hey, I want you to go turn this pump on, or I want you to energize 24 volts out to some device in the field, you do that with a CIP command that consists of what service you want to run, what class you're running it on, what instance you're executing that service actually against, and then sometimes what attribute that service is going to operate on. Maybe you're setting the value of a variable within that object. So let's talk about probably the most common, the most basic CIP object, the identity class. The identity class is instance ID 1, easy to remember. It has a default instance of that class, ID 1. And it supports a function, a service code of get all attributes, which is service 1. So, easy message to remember, 1, 1, 1. And that's going to tell you all the basic information about that device. So, we call that the who message. And in the who message, you're going to get things like the vendor of the device. And you can see, or maybe not because it's kind of cut off here at the bottom, but on the bottom, you can see this JSON payload here where I've sent a who message to a device using a Python tool. And it's returned to me the vendor, the product type, the firmware revision. It's returned to me the device status. Is it running? Is it faulted? Is it in some kind of configuration mode? It's told me the serial number of the device. It's told me the actual product name, the string of the device, which is on the end over here so you can't see it. But the who message retrieves all the information about the device from the identity object. And just like the identity object exists, there's hundreds of CIP objects within these devices, and all of them have a very specific purpose. They have very specific services which retrieve data out of them, or they perform functions within that object. And all of these objects all together make up your CIP protocol. So different devices will have different objects. The core specification says which ones you're required to have, which ones are optional, and most vendors throw all that out the window and just say, we're going to implement whatever we want. And so you're really up to the vendor to tell you what objects exist and why they exist and how to use them, and generally they don't like giving up that information. So, if we want to actually talk to one of these devices, access these CIP objects, there's 3 ways to do this. There's 3 forms of what we call explicit communication. That's where we're doing a request and we get a response from the device. There is UCMM. That's your unconnected message manager. And what that means, we talked about how CIP has its own mechanisms for things like routing and other network services that TCP already provides. So UCMM, that's kind of similar to saying, hey, I don't need a session. That's saying, kind of like you're sending out a UDP request and getting it back. That would be the equivalent in networking terms. Now, this is over TCP, but I'm creating a CIP request without a CIP session. And I'm saying, hey, do this thing, send me the data back. There's no CIP routing involved. There's no other CIP networking mechanisms involved. It's the most simple type of request. Then there's unconnected messaging, unconnected requests. Unconnected means I'm creating a CIP session. I'm creating a request. I'm using all of the capabilities of CIP routing, but I'm only going to do it for a single request. And so both sides know, hey, we spent all this effort. We set up a CIP route. We had multiple devices involved. I'm processing the request. I send you the response, and then we automatically destroy that connection. So it is a single session used for a single request. And finally, there are connected sessions, connected CIP requests, and that's identical to unconnected, but it leaves the connection open. So you can now reuse all of that information that you've specified for your routed path for any other network infrastructure you set up between those devices. They'll persist that connection. You have a session number, and you can reuse that session number. That session number is interesting because that is completely independent of your TCP session. Your TCP session can make or break 100 times, and CIP doesn't care. Your CIP session will persist. So you can see that layer of abstraction where we have duplications of infrastructure, scaffolding in our networking environment where CIP has its own versions of things like sessions and routing independent of TCPs. So let's talk about routing, because routing in CIP is one of the things that makes it super fascinating. CIP, because it is different types of networks, not just Ethernet, it has mechanisms in it to allow it to be backwards compatible with its predecessor networks. So here on the top, I have a CIP path. You can see IP addresses in there. That doesn't really look like a normal web path, does it? On the top, we have a Ethernet IP network. That's our SCADA network. This would be your process control network, perhaps, in your plant. And we're saying that we're some device. We're starting here, somewhere on our plant floor, and I want to connect all the way down here to a card in this PLC, a module that is in the chassis of a PLC somewhere completely else in my plant. Well, we can build out a path to do that because all these devices talk CIP. And we can say, hey, I want to talk to whatever device is 10.0.10.10. And that takes me to that Ethernet card in that chassis. I can say comma 1 to go out port 1 of that device, which actually takes me to the back plane of that chassis itself. I can say then go to slot 10, and that takes me to slot 10 in my chassis. From there, I say go out port 2. That's that purple 2. And that takes me out the control net port of that card. We've now transitioned from an Ethernet-based network onto a control net-based network. From there, I'm going to say go to node 4, which is my HMI down here. From node 4, I'm going to say go out port 3, which is the redundant Ethernet connection on that HMI. And then I'm going to say go to 192.168.1.1. That's my PLC down here at the bottom. That's its Ethernet card. And finally, comma 1 to go to its backplane, comma 5 to go to slot 5. I just sent a request from one Ethernet network that had no Ethernet-based connections to another Ethernet-based network by utilizing CIP routing. I traversed a control net network. I traversed 3 different devices to get there. Essentially, we took 2 networks that from a network topology standpoint looked like they were air-gapped, and we got a command between them. That's what makes CIP routing so fascinating, is the security implications of what you can do on these devices between networks. It's freely available. You can route between these types of networks all day long, and these devices do not care. So now we're going to talk about the fun stuff. Just a quick disclaimer. This is critical infrastructure. We are going to be talking a little bit about how to get started hacking critical infrastructure. So with that, we'll put on our blue team hats, not our red team hats, right? These systems do protect humans, right? When hacking into these systems, you never want to hack a live system. You could kill people, many people. These systems protect the environments. When hacking into these systems, there are catastrophic environmental consequences if you do something incorrectly. And finally, physical infrastructure itself. You could take down entire refineries, power grids. The astronomical impacts of these systems when they go down is quite large. So we don't do this for the sake of breaking into things because it's fun. We do this for the sake of knowing how to protect our critical infrastructure, right? Okay, there's the scary talk. Let's do the fun talk. Fuzzing. Everybody like fuzzy things? I like fuzzy things. My dog is fuzzy. Fuzzing is when we send targeted random values to a device through the protocol. So we talked about how we have these ID numbers for classes, instances, attributes, and services. They're just numbers. What if we selected some number ranges and just sent requests where we said, hey, I want to send a specific service. Maybe I'm going to use the get attribute list service, service 3, on every instance 0. An instance 0 is the singleton or static instance of a class. And I'm going to say do it on every instance number between X and Y. I'm just going to see what I get back. And that's a really common way to find out what C++ objects in my firmware are attached to the CIP protocol within that device. That gives me very quick and dirty knowledge of what actually is in there in the device. How do I find what functions I have available to me? Because there's no way to say, hey, tell me what you can do. The vendors don't want it to have that function, right? So it's not going to give you a list of everything it supports. You have to go find it. So fuzzing is a really cool technique to do this. So here's a fuzzing example. I've built a simple Python script here. I'm using service 03. That's get attribute list. I'm using class code of class ID, as you can see, which is in my for loop. And I'm saying, I just want to hit every class from 1 to 1,000. Let's just see what we can find, right? I'm using instance 0. I'm querying the singleton instance of these classes. And I'm using attribute 0, which is the null attribute, meaning I don't need an attribute in this case. At the bottom, you're going to see an output, a snippet of what this script returned here. And you can see we have a whole bunch of these destination unknown, class unsupported, instance, yada, 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 basically telling me, hey, there was nothing there. Good luck. Try again. But you can see we got 2 hits there. And I've put those in red boxes. The first one, class 0xa1, we got a service not supported. Okay, what does that tell us? There's an object there. It doesn't support the get attribute list service, but we know there's an object there now, right? So if we wanted to expand on our fuzzing, what we'd do is reset up our script to go hit every service code and see what service codes give us errors. That's good to know, right? We can now start pen testing that particular object and figuring out what it's capable of, what data it's storing. We got another hit, class AA. In this case, this is a known object that's actually part of the protocol specification. It's the Ethernet TCP IP object. It's the object that stores the device's IP address, MAC address, diagnostics counters for its Ethernet ports. And we got a service not supported from it as well. Well, that's easy. I'm just going to go get the spec out and say, hey, what services does this object actually have in it as part of the specification? Because I know this device now has that object. Now, granted, I'm talking to it on an Ethernet-based network, it better have that object. But the fact that it's exposing that object to me on the network means I can now access that object, I can query that object, and I can control that object. Because as part of the CIP specification, the TCP object allows me to remotely set the IP address of the device, change its gateway, change its subnet mask, without requiring any authentication mechanism. You could modify this script right here to go change the IP address of this device just like that, and the device would have a new IP address. So, that's kind of a quick and dirty intro into fuzzing. What do you do next? Well, in the Rockwell, Allen Bradley world, we have what we call a MNRF. Really fun word to say. That is a major non-recoverable fault. And it is the easiest thing to do to a controller. It's also perhaps one of the most dangerous things to do to a controller. A MNRF will stop whatever the device is from executing, so it'll halt execution. It will cause it to dump its entire configuration out of memory, so now it has no more program, no more configuration. It is just a dumb, dead box waiting for a technician or engineer to plug into it and give it a new program. That's dangerous because, as we talked about, these devices are running critical infrastructure. So you can imagine you have some computer in your plant and it's controlling the pressure on a pressure vessel that's at 10,000 psi, and all of a sudden that computer just halts, says, no, I'm done. And you might have some valve feeding that system, providing whatever product is going into that vessel. And if it can no longer say, hey, we're getting too much pressure, we need to close that valve, then that vessel is just going to overpressure and blow up. Now, presumably your mechanical engineering team has put some other types of safety mechanisms in place, like pressure relief valves or any other type of mechanism like that. Like generally these systems are fail-safe. So if one of these computers crashes, you have relay logic, and as part of the electrical installation, how these systems are wired, your valves should go to whatever their safe position is. Maybe you're venting that vessel. Maybe you're cutting off the flow of product into that vessel. But still, you have caused a disruption that very potentially could have major impacts. The reason MNERFs are easy to find from a fuzzing perspective is these systems do integrity checks on themselves continuously. And if they see that there was a failure to validate input and it caused a buffer overflow, the system's going to go, hey, I don't have data integrity anymore. I need to MNERF. And boom, it's gone. So you could presumably go through and during your fuzzing have given it a service ID that they didn't account for when they do their input validation. And all of a sudden the code goes off into some random branch that it's not supposed to go out into, and it fails that integrity check in MNERFs. In my experience, when I'm doing fuzzing, I can find on average 3 MNERFs a day. So that just tells you how often these MNERFs occur in these devices. I would say that I've spent many, many hours in Wireshark. I'm sure everybody here knows what Wireshark is. Wireshark has awesome, awesome capabilities at decoding CIP. I don't know who, but some poor soul spent a lot of time building the CIP plugin for Wireshark, and it's absolutely fantastic. So definitely utilize Wireshark. And that's it. So thank you. Thanks for coming. I'm going to leave you with a couple tools. So first, if you go to the ICS Village GitHub account in our CTF repository, every script and demo I used to build this presentation is in that repository. You can actually get that tooling to do fuzzing. I have fuzzing tools in that repository to get you started. You can also use the Molex Ethernet IP tool. This is a free tool provided by Molex. It's for doing device validation and testing. Awesome tool for this kind of stuff. And finally, if you're a Python guy and you just want to do it all on your own, PyCom 3 is a fantastic library. I am not the developer, but I know the developer. He is awesome, very open to suggestions. And I say just go to eBay, find some hardware. That's what I do. This stuff on eBay isn't cheap, but it's not too expensive. It won't break the bank if you want to have your own little cyber range at home. And finally, once you find something, report it to SysEvents. They'll help you get connected with the vendor, build those relationships for you, and that way the vendor can get it fixed. And that's it.
Cool.